Okay, so let us begin. Okay, for those who are new here, I am Ritojit Kundu. I am a PG student at IIT Kanpur, and I am one of your TAs for Advanced Condensed Matter Physics this semester. So for the next 2 or so hours, I'll be discussing some problems, so so that will help you in solving your this week's assignment. Okay, so for today, so is my audio, video, and screen, is everything okay? Can anybody confirm?
Yes, sir.
Okay, all right. So yeah, so today I wanted to talk about uh, so some things, like which we started last time. So so Hubbard model, some physics of Hubbard model, and then we'll talk about some Green's functions. Right, so that you will get some practice of writing out diagrams, how to. So if you are given a Feynman diagram, how do you write the expression for that particular diagram? uh, so you will also have some practice of Wick's contraction, and I will show you how to do Matsura summations. I'll show you the general theory so that you can actually take any expression, and if that has a Matsura summation, you can do that basically. So right, so these are the things that I'd like to cover for this time. Okay, and apart from this, if you have anything to discuss, feel free to just hop in. Okay, and at any point, if you have any question, you can just unmute yourself and ask. Okay, and it will be helpful if you have a pen and paper handy, so that you can also do these calculations along with me, so that you understand it better. Okay, so anyway, so let's just begin. So last week we actually talked about a little bit about Hubbard model. So the Hamiltonian of Hubbard model is given by, so as you know, the Hamiltonian is given by something like this. So you have some electrons that can hop between nearest neighbors. Ij are nearest neighbor, and summation over sigma as well. And on top of that, you have some interaction, which is the on-site Coulomb interaction. So which is between Ni up, Ni down. So this is a density interaction. Okay, this is a 4 fermionic term. So this Ni is, as you know, these are just Ci up dagger, Ci up, or this will be just Ci down dagger, Ci down. Okay, so these are just densities. Okay, and then there is another term which is the chemical potential. So the chemical potential actually fixes the number of particles onto your system. So that is given by, okay, so sum over all of such densities. Okay, so this is the general Hubbard model that we talk about. So these things turns out to be that these things are kind of very hard to solve analytically because of the exponentially large dimensionality of the Hilbert space. So for example, I showed you last time that if you have a chain of length L, and you put all of the spin up and downs in there with Hubbard interaction, then this dimension of this Hilbert space will be actually something like n to the power 4. So it will grow as n to the power 4. Okay, and if you do the math, it turns out to be for very small system. So for example, for very if you have n is equal to 10, so for very small system, you will see that to store all of the data of the Hilbert space, you need basically around 26 gigabyte. Okay, so that is kind of pretty huge, and you can see that it grows exponentially. You will add one more, you will see that it will actually not fit in any personal computer. Okay, you'll have to go to some supercomputer, some cluster and all. So these are really some kind of a monster, right? And so so I mean, it is very hard to solve this by exact diagonalization, but there are some approximate techniques which you have heard about, like there are mean field techniques, okay, which is used in studying ferromagnetism and antiferromagnetism and order in this kind of systems. So there are also other kind of numerical techniques which are called DMRG, density matrix renormalization group, and also there are quantum Monte Carlo, which actually works pretty well, okay, in some cases, okay, but so nothing fits for all of these cases, okay. So yeah, so I mean, these are very huge to look at, but but one can actually do some approximations to this, okay, rather than taking this exact model. And so these approximations are something like this. Let's say t is very small, t tending to 0. So t tending to 0 means that this u by t is actually infinity. Okay, so these are the ratio of two energy scales in my system. The u is the on-site Coulomb interaction and t is this hopping energy scale. So this is called a strong coupling regime. And then there is u tends to or let's say t tends to infinity. So it has only hopping. So this u by t is actually going to 0. So these two limits are actually well understood. Okay, so this is called weak coupling. So these two regions you can have some analytical understanding of these models, but as soon as you are in between somewhere like t is finite and u is finite, so it becomes very hard to solve the problem. Okay, so we'll not even try to solve this for any I mean for this kind of large or small systems, but so we'll try to have some insights of what is actually happening under the hood, right? So to do that, what we'll do is we'll study the single site limit. Okay, so this is something that we talked about last time, so but let me recap it for you anyway. So single site limit means that I mean, we do not have a chain, we have just a single site. Okay, so on top of this I can put single spin up, or I can put spin down, or I can put a double occupancy, right? Or I can also put nothing, which is the vacuum state, right? So why the single site is kind of very important to understand. So now I mean this is so let me actually try to give you some kind of arguments why single site is actually important to understand. So for example, so you know how does a band forms, right? So let's think about a thought experiment that we have actually atoms which are sitting very far apart. Okay, so when they are sitting very far apart, then we can kind of think that their wave functions actually don't overlap at all. Okay, so if their wave functions don't overlap at all, then there is no hopping. If there is no hopping, then if I just calculate the energy eigenstate of this system, then I'll just get only atomic energies. So E, let me call it E80 atom. Okay, so I'll only get E atomic energy scale. So for example, if you have, let's say, some spin half, right? So you will just get plus 1 or minus 1. Okay, up to scale. Only this kind of energies, and these are very degenerate. These are highly degenerate states. Okay, but on the other hand, if you bring this atoms or sites closer, so that they overlap, I mean they overlap somewhat, so that there is some hopping, so then the band actually emerges, right? So this is like a solid state physics 101. So this is how the band's formation forms. Okay, this is thought experiment. We do not actually do it like that. Okay, so I mean just this is a thought experiment. So this, in this limit there are just two bands. Okay, and in this limit the band actually becomes I mean these are like really, it has a bandwidth. Okay, so yeah. So now so I mean, to understand any kind of physics in Hubbard system, so we are thinking about a single site model. Okay, so that also means that we are not we are neglecting all sort of hoppings in between, right? So I mean that is a basic motivation to study the single site physics. So okay, so when you have a single site, so the Hubbard model is very simple. So there is no other site to hop to, so the tunneling is actually 0, right? So the Hubbard model in that case is just given by u I ni up ni down and minus mu ni sigma. Okay, so you see there is no tunneling, right? So this is the single site limit, or this is also called the atomic limit, right? So it turns out that we can actually solve this case. Okay, we will get so what we are trying to do is we're trying to find out what are the eigenstates of this Hamiltonian. So so as you probably know that the basis vectors of this Hilbert space are given by these four basis vectors, which is vacuum, so single up spin or single down spin, or doubly occupied up and down spin, right? So there is no other basis vector. So this actually spans your Hilbert space for the single site limit. So what you can do is you can actually calculate all of these matrix elements, right? So let's say 0 0 or h up up or h down down or down up, something like so. So the idea is you calculate all of these matrix elements. Okay, then you can write this in a 4x4 matrix form. Okay, so this is a 4x4 matrix form in that basis. Okay, so then it is easier to find the eigenvalues. Okay, so so let me actually do a little trick here before calculating the eigenvalues. So this is one form of the Hubbard model. Okay, so this is not actually particle hole symmetric. So we can actually add some constant terms into this Hamiltonian to make it particle hole symmetric. So you can check that. So if I write the Hamiltonian as something like this, so Hamiltonian is written as something like u I ni up minus half ni down minus half minus mu I sigma n I sigma. So this Hamiltonian is actually particle hole symmetry. Okay, so it is sometimes it is kind of easy to deal with this. So you will get energies which are even function, which are like, if you have some plus E energy, you will also have minus E energy, something like that. Okay, it also depends on chemical potential and all. But so let me actually take this Hamiltonian, and you can check that this Hamiltonian is actually same as this Hamiltonian up to some constant terms. Okay, so which you don't anyway bother adding any constant term, that basically shifts your zero of the energy. So yeah, so now in this basis we can actually write out all of this matrix element like I mentioned previously. Okay, we can find this 4x4 Hamiltonian matrix, and we can analytically diagonalize it, right? So it turns out that if you diagonalize it, so you get the eigenvalues which are given by this u by 4 minus u by 4 minus mu minus u by 4 minus mu and u by 4 minus 2 mu. Okay, so these are the eigenvalues, and these actually correspond to so you can find the eigenvectors also, so which is also quite easy to get. So yeah, so let me actually write the eigenvectors as well. So okay, so let me just make a table so that it is very clear. So now you can see from this thing, so if mu is 0, okay, so you get only plus minus u by 4. So in that sense it is actually particle hole symmetric. Okay, so okay, and the eigenvectors are given by, so this is the eigenvector, vacuum is the eigenvector of this, and then this is up spin, so this is down spin, and this is the double occupancy. Okay, so this actually gives you the full all information that you need to calculate any kind of observable if you want to look at any things, for example occupation or Green's function, like this will have every information. Okay, so
So when you know that, you can actually calculate the partition function, so which I'll be doing that. So is everything, I mean, can you, is there any questions you can just ask, right? Okay, so I can now write the partition function. So the partition function, as you know, is a trace of e to the power minus beta h, and so the trace, I can just directly use the eigenbasis to write out the trace, so this is just something like this, plus up spin e to the minus beta h. So these are the four terms that you will have in this trace. Okay, and as you already see that these are already in the eigenstates, so you can directly write the eigenvalues, right? So this is from something from Cayley-Hamiltonian theorem. So if some function, so if you have some matrix which acts on, so if the eigenvalue equation is something like this, so then this is generally true, that the some matrix f of m acting on v will give you just f of the eigenvalue times v. Okay, so I will be just using that, and then you will see that I just get something like this. Oh, I'm missing betas. Okay, minus beta minus this thing, minus beta minus this thing, beta u by 4 minus 2 mu. So this is the partition function, right? So given that partition function, I can find now various quantities of interest. So for example, let's look at this quantity called occupation. So I'm looking at the single sites occupation. So rho is in up plus in down, so the expectation value of this thing. Okay, so the expectation value, as you know, when I am talking about thermal states or density matrices, so which is given by this partition 1 by partition function trace of this object in up plus in down times e to the power minus beta h. So just this, right? So I mean, standard statistical mechanics, right? So this actually counts. So on this site, given a chemical potential, how much particle you can put. So this is the occupation. So similarly, like we did last time, we can expand our this trace in terms of this eigenbasis 0 0 up up down down and up down. Okay, and so let's actually quickly do that. So it is given by 1 by z. First term is 0, in up, in down, minus beta h acting on 0. So there will be similar other terms. Let me just copy and paste for all of this. So you can actually, I mean, calculating this kind of expectations are very easy. So why is that? Because this n actually calculates how many numbers or upspin are there, and n down calculates for how many number of downspin are there, right? So for this example, for the first term, so these are 0, right? So there is no up down in the vacuum, so the n up plus n down is 0. For this term, so n up and n down, this quantity is actually 1, right? Because there is one upspin. So n down is 0, but n up is 1. Okay, similarly this quantity is also 1, and this quantity will give me 2, because now there are one up and one down, and I am just adding them. So let's just write them out. and we'll also put this act this operator on these states, and we'll just write in terms of eigenvalues, right? So let's just do that. So now so rho is 1 by z 0 for the first term, and then second two next terms give the same contribution, so we'll write beta, so let me make it plus u by 4 plus mu, and then so yeah, plus 2 e to the power minus beta u by 4 minus 2 mu. So this is the result that we're looking for. So now this looks kind of complicated, but so if you, let's say, try to plot this thing, okay, so you can, if you cannot plot, you can see how does this function look like. You can just take a help of any computer, and you can probably plot this thing in Mathematica or Python or whatever that you want. So let's try to plot this quantity. Okay, so let's say this is my chemical potential, so I'll be varying the chemical potential, right? And then I am to calculate this occupation, which is given by rho. So let me first draw it out, so then it will be easier. Okay, so if you just plot this quantity, you will see that there are steps. So this is the temperature is actually almost 0. Okay, temperature is very small, so these are like clear steps. So you can see that if I increase chemical potential, so the initially I start with a 0. Okay, so that means that for very chemical potential which is smaller than minus u by 2, I cannot put any particle, because there is energy cost of putting that single particle. Okay, so I cannot actually put any particle, so that's why the occupation is still 0 up until minus u by 2. Okay, so as soon as I hit this u by 2, now I have the amount of energy that I actually need to put a single particle. So now after this I actually put a single particle. Okay, so that's why it goes up to 1, and then I also I again increase the chemical potential, right? But I see that nothing is actually changing. The density, the occupation is not changing at all. But then again I see that at certain energy u by 2, then I can actually put another particle, so that the total occupation becomes 2. Okay, so it might be little hard to understand from this kind of the particle symmetric Hubbard model, but let me actually write this in terms of a particle whole not symmetric Hamiltonian, so that it will be very easy to understand. So let me write this as E atomic and E atomic plus U. So E atomic means what are the states, what are the eigenvalues that the single Hubbard site can take, and then U is the interaction, and this gap is this amount is U, right? So you can see that initially I can put a particle. So let's say I have some level EAT, and let's say I am putting some up spin, right? So then if I increase the chemical potential, then I can only put another particle which has to be opposite spin at EAT plus U. So you see that, because so this additional energy this U is actually because of there is additional cost, Coulomb cost, to put another particle. So so that's why this other level has EAT plus U. Okay, and this kind of levels are actually very different from how you think about single particle levels, because this the other level, this is actually occupation dependent. Okay, so the meaning of which is if I started with this kind of picture, let's say, let me write it as EAT and EAT plus U, I cannot put any particle at here because this level doesn't exist yet, but I can put a particle here if my lower eigenstate is that have a particle. Okay, then I can put a particle with additional cost of U. So that is the meaning of this occupation diagram. So we see that when I have this EAT, this amount of energy, then I will put one particle on the lowest band. Okay, after putting the particle in the lowest band, this level gets created, right? So then another particle I have to put with additional u cost, and then my occupation goes to 2. Okay, so let me draw it here as well. So there is there is no particle here, then there is, let's say, upspin, and then I can have double occupancy, right? So these are this occupation, these are the meaning of these occupations, right? So any questions? Because we'll be actually when basing on this concept, we'll actually introduce another interesting thing. So any questions? So I mean, based the one thing that you'd like to remember is that these are not like single particle bands. For example, so in single particle, let's say I have some band, right? Let's say, and I have some other bands also. Okay, so you can actually put any particle anywhere, and this band is always there. Okay, this band is always there at high temperature, or if you're not looking at ground state, you can put any particle here. But the case here is actually totally different. The other level doesn't exist until you put a particle first. So there is a occupation dependent levels, energy levels, right? Yeah, so that is what I wanted to highlight. Now, so these have actually, this step like feature has a name. These are called Mott steps, not mat, Mott. So these are called Mott steps. Now, so I mean, you will get very sharp steps if your temperature is very small, almost 0. Now as you will crank up the temperature, you will see that this will get little bit smoothened, like this way, and something like this. Okay, but the steps are actually there. I mean, there is clear distinction between occupation number 1 and 2 and so on. Now, so there is something called a charge compressibility. So which is given by this kappa is equal to del rho del nu. So charge compressibility is given by the rate of change in occupation as you are changing the chemical potential. Okay, so this is basically a tangent of this curve of this curve. So tangent of this curve. So you can see that the tangent here is actually, the tangent is 0, so the kappa is actually 0. Okay, so these are people can actually experimentally measure this charge compressibility, and so the charge compressibility 0 means that you have a gap. Okay, gap in the spectrum or something like that. So yeah, I just wanted to highlight that. And yeah, so similarly, like here we calculated occupation, you can also calculate other quantities of interest. For example, you can calculate local moment. So the local moment is given by some m square, and m square is the difference of n up minus n down. Okay, so like these are also, you will calculate with the partition function 1 by z trace the operator itself into the minus beta h. Okay, so this is how we will calculate it. And so if you can actually expand this quantity, and it becomes something like this: n up square plus n down square plus 2 n up n down. So now for fermions, the n up or n down is just 0 or 1, right? So squaring it or not doesn't make any sense, so we can actually remove the squares. So it is just n up plus n down. So this is just n up plus n down plus 2 n up n down, right? So n up and n down, this expectation value is the occupation that you calculated just now, and then there is oh, okay, this will be minus, and there is some quantity d. So okay, so you can actually calculate this d easily. So I'll not calculate d. I mean, you can take it as a small exercise, and you can calculate what this expectation value is. Okay, so this is also, I mean, what is the moment at that particular point. Okay, so this is single site Hubbard model. So we can actually go beyond the single site atomic limit Hubbard model. So what do I mean by that? So okay, so let me pull up a new page. Okay, so these are the let me actually summarize what we have done till now. So in atomic limit, so electrons are not actually hopping from one side to the its nearest neighbor. So we have basically two energy levels, E atomic plus E atomic plus U, right? So these are the two energy levels, and I can put one spin here and another spin here, right? So and the gap has to be U, and gap between these two systems has to be U, and these states are like very degenerate. Okay. So now when we'll introduce the hoppings, we'll see that this degeneracy is actually lifted. Okay. So okay, and before that, so we can actually plot the density of states for these levels. Okay, and this, as I said, that this has a large a density of states, a large degeneracy. So you expect that these states are highly this will have diverging density of states. So this is your density of states, and this is your energy. So let's say at EAT and EAT plus U, so you have actually a Dirac delta function going to infinity, something like that. So you have two just very sharp density of states. Okay, now what we will do is we will actually introduce hoppings. So when you will introduce hopping, so this degeneracy will be actually lifted. Okay, and so you probably know from I mean how when you calculate bands, you see that when you introduce T, then the atomic levels actually expand, and they become a finite bandwidth thing, something like 2T cos k, something like this, right? So as soon as you introduce T, so that gives you a 2T bandwidth band, right? So this is the same thing that you expect here also. So as you will increase the as you will make the T non-zero, so what will happen is I will see that these bands, let me make a copy of this. So this is one of the band, so this, and another band is something like this. Okay, and so these Dirac deltas, Dirac deltas of this density actually vanish and become somewhat like this bell-shaped kind of density of states. Okay, so the density of states have a bandwidth, right? So this bandwidth, so you can measure this bandwidth of these bands. So this bandwidth is actually given by 2TZ. So where this Z is the it's called somewhere, it is called the coordination number, or it is the number of nearest neighbors. So just let me write it, number of nearest neighbors, Z. So similarly, this lower band also have this bandwidth of 2TZ. Right, and so this gap is still U. So this is still U, right? And now you can define another energy scale which is called the gap. So now gap is delta. So delta is charge gap. Okay, so you can see that, I mean, you can probably now see how do you get this kind of band structure, right? Band kind of things. And but still you can see that so let's say so this is my Fermi surface. Let's say this thing, so this energy level is my Fermi surface, EF, or Fermi energy. There is no Fermi surface yet, so this is the Fermi energy. And if I calculate the density of states or occupation at EF, we'll see that this is actually 0. So this is density of states at EF just. So density of states at EF is actually 0, which indicates that this is actually an insulator, right? So So but this is actually a rather kind of weird insulator that you already have seen. So you have, till now you have seen band insulator, right? So you have some kind of band structures and something like this, and if your chemical potential is somewhere here, or this is your Fermi energy, so you see that I mean there is a gap, right? And if there is a gap, then this is called an insulator. Okay, here also the same concept actually is still there. The density of states is 0 at this Fermi energy. So you can also have metals, something like, let's say, this, where the Fermi energy is given by this. But clearly you can see that there are states here, right? So states, some states are here and here. Okay, so the DOS, the density of states, is actually non-zero for this thing. So this thing are called metals. So these are band insulator and band metals, right? But here, so the other thing that I showed you is that this is not like a band insulator. So this is something which is coming from interactions. Okay, so in the sense that if this band was not filled at all, this state was not there. Okay, so you could not even try to put a particle here. First you have to fill this whole band, and then only you will have access to this band. Okay, so this is the most weird thing that that you can think about this kind of Hubbard insulators. So these are like insulators, and this is something called a Mott insulator. Right, so yeah, let me actually draw a clearer picture. So I have this two and these are called Hubbard subbands. Okay, so let me just annotate all of these things. So this is given by U. So this is the charge gap delta, and so the bandwidth of these things are given by 2Tz, right? So now so this apparently this U and T are actually different. They're independent variables, right? So for different materials they will be different. But let's say if you get something like this, U is actually greater than let's say Tz. So then you will see that this gap will always be there. Okay, if your interaction is very strong, then this charge gap is always there. So there is no density of states at this level, at the Fermi energy. Okay, so I mean in this case what you get is just an insulator. Okay, so this is called the Mott insulator. So on the other hand, I can also have a case something like this. So let's say this, and these are my initial Dirac deltas, and after adding the dispersion it actually has a bandwidth. The another one has a bandwidth. Okay, so now if you look at the Fermi energy, which is let's say somewhere here, so you see that the density of states is actually not zero. Okay, so then this is actually metal. Okay, so metal which is coming from a small interaction. So the interaction scale here is given by U is actually somewhat of the order of T times Z. Okay, so when these two scales are same, you will get a metal, or let's say, let me write it like U is smaller than Tz. So then the two Hubbard subbands will overlap, and you will get a metal. Okay, and there is actually in between these two limits there can be another limit. So let me so the intermediate limit can be something like this, that the two Hubbard subbands just touch. Okay, for example, let it be like this, and then let it be like this. Okay, So this will happen when u is of the order of t times z, right? So this was an insulator, and this is a metal, and you see that there is actually a transition at this point. Okay, so this is called a Mott transition. So Mott transition takes a metal, takes an insulator and makes it a metal. Okay, so yeah. So any questions? So this is actually very phenomenological, so that I have not done any mathematics, just to I mean, give you some idea about this very interesting physics because of interaction. So is there any question?
No, sir.
Okay, so okay, let's actually move on and do something somewhat simpler than this Hubbard models. So let's actually talk about Green's functions. Okay. So I think you have gone through the week 4 and 5, I guess. So you have learned a little bit about Green's functions. So actually Green's functions, so there is a, when you talk about Green's functions, there are a whole plethora of Green's functions. Okay, so for example, so there is something called, so when you write a Green's function like this, let me write a very simple version, r sigma t r prime sigma prime t prime, so which is given by minus I time ordering of psi sigma t. So these psi's are field operators, psi sigma prime r prime t prime expectation. So this has a very nice physical intuition, right? So this means that, okay, I have created a spin sigma prime at r prime t prime, okay, and then I let it propagate, and then I annihilate at this point, and I calculate this amplitude. Okay, so as simple as that. So this kind of Green's function, when you have a time ordering, it is called a causal Green's function. Right, so this is one important object that you will see appearing in many parts in condensed matter physics. So, and there can be another Green's function which is called a retarded Green's function, right? So it is like minus I theta t minus t prime, and then I'll have expectation value, and depending on whether I am writing this Green's function for boson or fermion, I'll have commutator or anti-commutator correspondingly, right? Sigma t comma plus minus. So I'll just write it as plus minus. So plus means anti-commutator, which is true for fermions, and minus is for commutator for bosons. So this is your retarded Green's function, right? And you see that, I mean, you can try to understand why is it called retarded. So it is called retarded because of this theta t minus t prime, right? So this is actually non-zero only when t is greater than t prime because of this Heaviside theta function. Okay, so, and before that it becomes just a zero. Okay, so this is called your retarded Green's function, and then you have your advanced Green's function. And yeah, obviously commutator or anti-commutator depending on fermion or boson. So here also you can see that this actually vanishes. So if on the other limit, so if t prime is greater than t, then only you get non-zero advanced Green's function. Okay, so there are also other set of Green's functions which are important. So just let me mention this. So these are called greater Green's functions. T, so which is given by I think minus I psi r prime t prime sigma prime. So this is called greater Green's function, and this is called lesser Green's function. So there is a reason why these are called so lesser or greater Green's functions. So if you expand this time ordered product, right, so time ordered product, so you can expand this out, the time ordered product. So this will give you basically two terms, so minus I, and so then there will be two terms, which is theta t minus t prime phi sigma r t, and there will be another term, so t prime minus t phi sigma prime sigma rt, and there can be my plus or minus. Okay, and you see that this so apart from these theta functions, so this part is the greater Green's function, right? So this is just g greater and this is g lesser. So that's why these are called greater or lesser, because this only happens when t is greater than t prime, and you will get lesser only when t is less than t prime. So that's why, I mean, greater or lesser, I mean, just a kind of terminology people use. So here I have written this in a basis, in a spin and position basis, something like that. But this kind of structure is actually true for I mean, if you write it in any other basis. Okay, for example, you can write it any other quantum numbers, right? In terms of quantum numbers, for example, you can write something like this, g r. So let me write the retarded function. So this is given by minus I. So here this, okay, so let me be a little bit careful. So this is nu. So nu is a quantum number. So in that case, the structure will be exactly same, but the field operators will have this nu index now. Okay, let me write it nu prime, or let's say these are just okay, or let's say these are fermions or bosons. So these are my creation and annihilation operators, right? So the structure remains same, but we just write it in terms of other field operators, okay, which here is the field operator corresponding to the quantum number nu and nu prime. Okay, so for example, if you want to, let's say, write a Green's function for a hydrogen atom, then it is very simple. So you can just generalize this thing to be something like this. So it has three quantum numbers, so n, l, m, and also a sigma, right? n, l, m, and sigma, and let's say t, and I can have n prime, l prime, m prime, sigma prime to t. Okay, so then I'll just directly write it like in the previous case, t minus t prime, and then because these are electrons, so I have anti-commutation. So c n l m sigma at time t, c n prime l prime m prime sigma prime t prime dagger. So this is the Green's function, if you like, for hydrogen atom. Okay, so I mean, just to show you that there is some vast, I mean, there is a plethora of Green's function that people use, and they appear at different context in quantum field theory or condensed matter, right? So yeah, so whenever you see these names, so don't be actually afraid, like what kind of thing are these are like very, like, really simple. So a reference for this is actually a very simple reference that from where I learned myself, is called a book by Radhi Ajishi. So that is a very simple and useful book if you want to learn about this kind of Green's function. Has a very simple introduction and all. So anyway, so yeah, so these are different sort of Green's functions that you can have. Okay, and it turns out that if we have so I mean, till now we are actually writing everything in real space, right? So r and t. So in r and t, so these are not very easy to deal with. Okay, so when you have this this position and time, as if these fields are function of position and time, then whatever you write, I mean when you write a Feynman diagram, it becomes an integral equation. Okay, and things become kind of hard. But so if your system has homogeneity, for example, I mean that means if your system has translation symmetry, so then momentum is a good quantum number. Okay, and you can go to Fourier transform this whole Green's function and you can go to momentum space. So it becomes very easy in momentum space to deal with these Green's functions, because in momentum space these are just algebraic functions. There are, I mean, all of the integral equations, all of the convolutions become just algebraic kind of things. Okay, so let's quickly see I mean how to exploit homogeneity of the system. So let's say we have this retarded Green's function x prime t prime. So I'm not writing the spin index anymore because that is just a trivial generalization, so you can try to do that, but let me actually ignore the spin for now, and then it becomes minus I theta t minus t prime, and these are fermionic field operators, so I'll write anti-commutator. Right, and this is a dagger. Okay, so you probably already know that. So when you have a field operator which is a function of, let's say, x and t, then you can actually write it in terms of some wave function amplitudes, right? So phi k x and then c k t, something like that. Okay, so these are wave function amplitudes, and these are annihilation operators of corresponding to that particular wave function or particular state. So if you have like a homogeneous system, then momentum is a good quantum number, and you can actually write so then the phi k of x, this becomes very simple. So this becomes just e to the power I k x by square root of volume. Okay, so as simple as that. So we'll just plug that thing here. So this is our psi xt. So this kind of expansion is sometimes in quantum field theory, it is called as mode expansion. Okay, but yeah, anyway, so the main thing that you want to take from here is that if momentum is a good quantum number, then the amplitudes are just like this. But if momentum was not a good quantum number, then you would have to take some another wave function. Okay, but as we are assuming that this is a homogeneous system, we are good with this. Okay. And similarly, you can also try to write for psi dagger. So you will just get something like this. So you can see that so these two equations, they look like just Fourier transformations. Okay, Fourier transformation. So this psi and this ck, these are actually Fourier conjugates to each other, and this is your Fourier kernel, for Fourier transformation kernel, if you like. So similar thing is for psi dagger and c dagger, which are like Fourier conjugate variables. Okay, so you have these two equations, and we will plug these two equations in this expression of retarded Green's function, right? And we will try to go to solve and see what do you get. Okay, all right. So yeah, so let's just do that. So g r x t is given by minus I right. So now we can plug in this psi and psi daggers, right? So let me just so I'll just put a v directly, because I have two square root v's which make up this v that I have written here. then I have two momentum summations. So because these are dummy variable, momentums are dummy variable of the summations, I will just I'll just take k1 and k2, right? And then I'll have e to the power ik1 x and e to the power minus I k2 x prime, and then I'll have this rest of the anti-commutator ck1t and ck2 t prime dagger, right? So I've just taken these two mode expansions and I've just plugged it in here. That's what I've done. So now you can probably simplify this thing a little bit. So let me actually do a manipulation in this exponential phase factors e to the power I k1 x minus x prime. So I am just adding this part, and I'll also have to subtract it, right, so that it is the same as I k2 minus k1 x prime. So you see that, so this part will actually cancel with this part. So this k1 x prime and minus this k1 x prime will actually cancel each other. So this is just a little manipulation, right? And then I have the rest of the anti-commutator. Right. So now so let's do another trick. Let's say that we are moving our we are changing our variables from x to x plus capital R, and also that that is happening for x prime as well. So this R is some constant distance, any distance. Okay, so if we do that, you see that I'll get something like so most of the terms will be same, but I'll have, okay, so this k1 x minus x prime, this is exactly same because plus R cancels from both of this x and x prime. But then I'll have this thing minus I k2 minus k1, so x prime plus R. So so now I'll argue that because our system is homogeneous, then any correlation that you can calculate that should not depend on any single variable, it should depend on a relative distance. For example, you can see that so this is a relative distance between x and x prime, but so in this part actually another R appears. Okay, so that means that this thing has to be 0, right? Because in any homogeneous system this term cannot simply be there because it depends only on a single coordinate. So for this thing to be 0, what I will have to do is, so I'll say that this can only be non-zero if k1 is equal to k2, so that this whole phase factor actually vanishes. Okay, so that will actually give me a direct delta, or let's say Kronecker delta here, k2 comma k1. Okay, so that I'll have this homogeneity. Okay, so I'll preserve homogeneity, and then I'll see that it actually make my life a lot simpler. So I have k1 k2, I'll put this k2 k1 here, and then so the other term is actually gone. So I have ck1 t ck2 dagger t prime. So now I'll do a, let's say, summation on k2, and I'll just change k1 to k. So this thing is just e to the power I k x minus x prime, then ck k dagger t prime. Okay, so now if you look at this expression carefully, you see that if I just keep this 1 by v out, and I'll just keep it to the power I k x minus x prime, then the rest of the term I can just directly write it as some gk function of t and t prime, right? So this is, you can see that we have started from a real space Green's function, and I have used the homogeneity of the system, and I have actually reduced it to a Fourier transform, right? Just a Fourier transform. So this gk t prime is given by minus I theta t minus t prime, and then this expectation, right? So it turns out that this is a Green's function in momentum space. Okay, so I've just gone from one, like the real space, to momentum space. Okay, so and you can probably see that these things are so it might be easier to deal with them. So you'll see how to how do we write the Green's function explicitly. But you also see that normally what we know is we know that if we write some ck and ck dagger, or let's say k prime dagger, then this is delta k and k prime, right? So this is the anti-commutation relation for fermions. But if you plug in t and t prime, then this is actually not true. So I mean, so if you plug in different times in this annihilation operator, then this is not true. There are additional factors. So this is not equal time anti-commutator. Okay, so we cannot use the anti-commutation. So we'll have to we need some another information for this thing, and to simplify this thing even more. So let's say I have a Hamiltonian, okay, which is written in terms of this momentum. So the Hamiltonian is given by, let's say, E of k and ck dagger ck. Okay, it's a diagonal Hamiltonian, and if it is a diagonal Hamiltonian, then you probably remember that the time dependence of this annihilation and creation operators are just like this: psi epsilon k t ck, and also ck dagger, the creation operator, is given by I epsilon k t and ck. So this is the simplest single band Hamiltonian that you can think about, and the ek can be something we don't care about ek now. Okay, so ek can be any so for example, ek can be 2t cos k that we have for just a single chain, or 1D chain, okay, or something like that, but we don't actually care about that now. So now as soon as I've written this, I can actually plug this thing into this, right? So because I know the explicitly the time dependence, so so this Green's function actually becomes and then I'll have these factors, so I can just drag them out. ck and ck dagger. So you see, by doing this, I have actually reduced this anti-commutator, which is not on same time, to equal time anti-commutator, right? So, and we know that this equal time anti-commutator is actually just 1. Okay, so the Green's function in time k t t prime given by minus I theta t minus t prime e to the power minus I e k t minus t prime. Okay, and you see that in this Green's function, okay, so one important thing I forgot to mention, that so when you have a Hamiltonian like this, so this is basically a non-interacting Hamiltonian. So all of this next steps that I am doing is true only for non-interacting Hamiltonian. So but for interaction, you cannot even have a closed form, so you have to do some approximation, but we'll not thinking about interacting Hamiltonians now. So this is the form of your non-interacting Hamiltonian, and we see that the time arguments t and t prime always appear as a t minus t prime. Okay, so that is that is, I mean, that comes because the Hamiltonians are actually not time dependent, so you have time translation invariance also. So that means that if you change t to be t plus some capital tau, or t prime to be some capital tau, so t minus t prime goes to t minus t prime only. Okay, so we can forget, we can write this Green's function as a function of t minus t prime. Right, and we can let's say take this, okay, we can change this variable also, t minus t prime goes to t. So then our Green's function has a single time dependence, I theta t and e to the power minus I epsilon k t. Okay, so as simple as that. So now we can actually do another one more simplification. We can go to frequency space. In frequency space, Green's functions look really simple, very simple. So to do that, what we have to do is we have to do a Fourier transform, right? So the Fourier transform, so gk of omega is just a Fourier transform of gk of t. So there is integration going from minus infinity to infinity, and e to the power I omega t, and so g k of t. Okay, so this is my gk of omega. So Green's function in frequency space. Okay, so I can just plug in the gkt omega t. So I'll have just, so I'll put the minus I outside, theta t e to the power minus I epsilon kt. Okay, so this theta t, as you know, these are Heaviside theta functions, so that will be 0 if t is less than 0. So that actually reduces my limit of the this integration. It makes it 0 to infinity. Okay, so dt e to the power I omega minus epsilon k t. So this is just the simplification has given us just this term, and you can all integrate, do this integration. This is integration of an exponential, but it turns out to be that at t is equal to infinity, this is a highly oscillatory function, and this will become ill-defined, right? So we do a trick. We actually put in a convergence factor on this exponent. So the convergence factor I'll just put here is, so this is just a little trick that we always do, so which is I delta. So I'll just put another I delta. So delta is actually a very small positive number, so that delta times t when t will be infinity, so that this delta time t, okay, so there is I, and I is also outside, so it is actually just minus delta t. Okay, if you just take, just take what is the sign of delta t, so then this becomes actually minus infinity, and e to the power minus infinity is just 0. So this is to make sure that the integral is well behaved and it converges, right? So yeah, with that trick we'll just do this integration. So this is just 1 by I omega minus epsilon k plus I of delta, and on the top we have I omega minus epsilon k plus I delta t, and the limits goes from 0 to infinity. So as I mentioned that at infinity this is just 0, so the first limit is 0, and the other limit is just 1 by I omega minus epsilon k plus I delta. So okay, so if I just do this one step simplification, and then this becomes omega k plus I delta. So this is your g retarded k and omega. So you have actually done a full, it's a double Fourier transformation. So you have gone from real space to momentum space by exploiting the homogeneity of this system, and you have also gone from time space to the frequency space by exploiting the time reversal symmetry, time translation symmetry of this system. Okay, and whenever all of these conditions are met, then the Green's function is basically just like this. So it is just a some function, right? So a very, very simple thing. So it doesn't have any commutator or anything, so it is just a function. Okay, so yeah, so this is how your retarded Green's function looks like. So any question or any comment if I'm going slow or fast, or any comment.
Sir, sometimes the heap side function has an integral
Right,
representation.
yeah, you can
Yeah,
also,
we can also do that,
yeah,
right?
yeah,
I
yeah, yeah,
mean,
yeah, there are multiple ways of doing this, you're right. So you can represent this heavy side theta function. So that is the opposite way that what I did. So I actually defined the Fourier transform like this, right? So if you don't want to define it like that, you just can introduce the integral definition of this Fourier, this heavy side theta function, and you can also get the same result. So that is the same. So I mean, what I am showing is not the single way of doing it. I mean, whatever you prefer, I find this is the simpler way than introducing. There you have to remember what is the integral representation of the heaviside theta function, but here you don't have to remember anything basically.
yes.
So yeah, so the Green's function becomes kind of very simple, right? And any Green's function, so on the other hand, if your Hamiltonian is not a diagonal Hamiltonian, so let's say Hamiltonian is something like this: Tij Ci dagger Cj, and Hermitian conjugate, something like this. Okay, so what will happen is, um, so you can so first thing you will try is, if these are in real space, Ci Cj, these are like lattice site indices, so you will try to go to momentum space. So if you go to momentum space, this is very simple, 2t cos k ck dagger ck summation over k. But if you cannot go to real space, then also the Green's function's definition is actually kind of same. So then momentum is not a good quantum number, but your Green's function will have matrix elements, right? So it is something like, let's say, Gij, okay, and it can be a function of omega. So because there is no time explicitly in this Hamilton, then this will be a function of omega, and this becomes omega times identity minus h plus some I delta times identity, its inverse, and then the ijth element. Okay, so I mean, it always have this kind of a inverse structure, omega minus h. Okay, but if you are not dealing with a diagonal Hamiltonian, so then you will have to actually evaluate this inverse. But if you're dealing with a diagonal Hamiltonian, then it is just like this, it is just this, right? So yeah, so any other questions? So if not, so let me, so these Green's functions are actually very useful objects. So you can actually use these Green's functions to calculate observable expectation value of observable. Okay, so relation to observables. Okay, so I'll show you how does this Green's function enter into the expectation values. So actually, let me take a just I'll be back in a single minute. Okay, so just. Okay, so I'm back. Yeah, so and anyway, I'm just doing a lot of algebra, as you can see. So it might be hard to follow it, but
once you have some time, you can actually look at this carefully. So I think now you have access to all of this notes. You know the links to these notes, right? So it is on the course webpage. So can you have so have anyone seen this link to this resources, like this note or this recorded video? So I mean, if you have not seen that, you'll find that it is given on the courses webpage. Okay, you can have access to this notes also. I'll just upload it today. Okay, so I'm audible, right? Just checking.
Yes.
Okay. So how do you how do you see that what are the relations to these Green's functions? So for example, let me take any single particle operator. For example, it can be something like this. So I do not have any specific operator in mind. So what I am trying to do is I'm trying to write a generic observable, and then we can actually put, so J is a placeholder, so I'll just put spin or density or kinetic energy to calculate the expectation value. Okay, so let's say the observable is given in terms of a density Jx. Okay, and this x is actually integration over whole space. Okay, I'm not writing any d here, but so by dx means that I have actually volume integral. Okay, in whatever space I am, so I have a volume integral, and this Jx has a second quantized representation which looks something like this. So these are field operators psi alpha x, and then J alpha beta x and psi beta x. Okay, so psi alpha and beta are field operators, and alpha beta are some quantum numbers. They can be any quantum number. Okay, so this is the structure of a single particle operator, and what I want to calculate is, and to calculate the expectation value of this thing, this density. So it is given by like I'll just take expectation value on the right hand side as well. So and all of these things are actually time dependent also. So yeah, so these are same time, equal time things, xt and psi beta xt, and this J alpha beta, this is just a function, so I can just take it out of these expectation values. Okay, so now let me introduce let me do a trick, something like this. So I mean, yeah, so I have written the same thing, but actually I've introduced this x prime and t prime here. Okay, and if you just take this limit, you will see that you will just go back to the last line. Okay, so you will see that why I'm doing this very soon. So yeah, so you see that okay, so let me actually remind you, so what does the Green's function look like? So the Green's function, so basically what I want to relate this thing to a Green's function. Okay, so the Green's function has structure something like this. So I g alpha beta x t x prime t prime is given by time ordering of psi alpha x t and psi beta x prime t prime expectation value, right? And this time ordering means that this has two parts. So psi alpha xt and psi beta dagger x prime t prime whenever t is greater than t prime, and I also have psi beta dagger x prime t prime psi alpha xt whenever t is less than t prime, but I have depending on whether this is a Fermi-On's or boson, I have plus or minus. So this is a causal Green's function that I told you about a little ago. So we see that this actually matches with this part, right? So but the alpha and beta, these two indices are actually flipped. Okay, so what we'll do is we'll directly
so let me also do this thing that t prime is t plus, so that I can actually really use this definition. Yeah, probably this is okay. So then I'll just in place of this expectation value of the field operators, I'll just directly put uh, the Green's functions. So x goes to x prime, or x prime goes to x, and t prime goes to t, something like that. And then I have so alpha beta times plus minus I g or let's say j alpha beta x t, or there is, let's say, no t, and g beta alpha x t x prime t prime. Okay, so so this is expression in terms of the Green's function. Okay, so like as soon as I have introduced some another coordinate which are same, so which is same as x and t, so then I could write instead of this expectation value, I could write a Green's function. Okay, so that this is a Green's function. And so you can see that this is basically a trace, right? So this is alpha beta and beta alpha. So whenever you have this kind of a matrix structure, you directly know this is a trace. So I can actually write this t goes to t prime, t prime goes to t, and then this is just a trace over j x times g x t x prime t prime, right? So this is the expectation value of j of x. Okay, and if you want to, okay, so this is the density average, right? Jx is the density of the observable that we are talking about. And if you are trying to look into what is the value of this total expectation value, then you have to just put this thing back in the integration, and I mean just this is the expectation value. Okay, so you see that this single particle observables, this quantity is very easy to calculate. Okay, now I didn't mention any operators, but now I will just plug in different observables, right, in place of this j. So for example, so if I am looking into a density, just number density expectation, so what I will do is, so number density is just like a identity operator, right? So because nx is just psi dagger psi, so nx, if you remember, is just psi x dagger psi x. Okay, and there is nothing else. So when basically the matrix for the nx is just identity. Okay, so nx average is given by plus minus I trace of just the Green's function. So you see that very easily, if you know the Green's function, you can directly calculate the density expectation. Okay, so you can also calculate the sigma, the spin density expectation, so which will be something like this. So plus minus I, so you see, and I am using the same formula again and again, but instead of putting, I mean, I'm just changing this matrices. So now this is sigma and g x t and x prime t prime, the trace of this whole thing. Okay, so you can go on, you can calculate what is your kinetic energy. So kinetic energy is given by something like this, plus minus I dx, and then limit x goes to x prime, t goes to t prime, and minus h bar square delta square by 2m. So this is my kinetic energy operator. And because this is I mean, this doesn't have a matrix structure, so I can actually take this out of this trace, and then I am left with the trace of Green's function, xt x prime t prime. Okay, so this actually is kind of very handy, I mean, if you want to calculate some expectation values. Okay, so I have shown you how to calculate single particle observables, expectation value of single particle observables. So you can similarly extend this to two particle observables, but which is somewhat involved. So there are much more steps involved. So I'll be not doing that, but if you want to look into those, you can look at this the reference of Ashcroft-Marmin, no, not Ashcroft-Marmin, it is Fetter and Waleka. So they have a section called relation to observables. Okay, so yeah, so this is a, I mean, very kind of useful section that you can have a look. So is there any questions? So
And this J is also for evaluation of current density, like
So J,
current density.
current density you can, yeah, so current density you can also, right? So this J is actually, I have not mentioned anything, so this is J is not current density here. I mean, this is actually any operator that you can think about.
But it can also do for current
Yeah,
density.
yeah, you can also do for current density the exactly same way. So you'll see that
In
when you
some
have,
non-linear optics paper I've seen, like in GA is used, and
yeah,
I was
yes,
not
current,
known that there was a green function involved also.
yeah. So Green's function, I mean, you don't have to write this in terms of Green's function, but so the point I'm trying to make here is, so if you know the Green's function, then you can very easily calculate any expectation values. Okay, so Green's function appears in the single particle expectation values. So
Yes, sir, I have some other doubts also. Like,
yeah, yeah.
is it useful for the linear response theory, and does this green function also work for non-linear
Yeah,
phenomenon,
yeah,
or
yeah. So
like
any kind of this linear or non-linear, this kind of response when you calculate, so the Green's function, yeah,
Kubo will fail, something like
right,
that.
right. So in any kind of this linear or non-linear response, the Green's function is a very natural language to work with. The Green's function and Feynman diagrams are very natural things to work with. They are very simple objects, and you can actually draw diagrams and work out a lot of details. Okay, so Green's function is you have to use there. Otherwise, you will have to do a lot of algebra. Okay,
Okay.
so yeah, so we will probably do some calculations of linear response for so Kubo linear response as well. Okay, so I mean, so let me emphasize again, this is true for any single particle observable. It can be current density, it can be spin density, it can be anything. Okay, so it can be magnetization or anything. So whenever you have some single particle observable, if you have the expression in terms of second quantization, you can actually get, you can write, you can put the Green's function directly and you can get out the expectation value. Okay, so you can think about it this more, and if you have many questions you can ask me next time as well, or yeah, or in the forum as well. Okay, so any other questions? All right, so okay, so let's move on to the next thing that I wanted to talk about. Yeah, so I actually wanted to talk about a little bit about Wick's theorem. So you have already learned Wick's theorem, right? So Wick's theorem tells me that, okay, if I have some string of objects, some A, B, C, D, and so on and so forth, I can actually reduce these things in terms of contractions. So like all possible contractions, so A, B, C, D, or I can do a contraction between AC and BD and so on and so forth. Okay, so the result of this kind of expectation is the summation of all such contractions that you can have. So this is basically the gist of Wick's theorem. So I'll not go to the derivation or that, those are very involved things, but I'll just give you some examples so that you get a good understanding for the Wick's theorem. So for example, let's say we have some expectation value like this. So let's call it A, and this is a time ordered product, k sigma tau so this is some expectation value. Okay, so we don't need to know that where this is coming from, but let's say this is what you are given and this is what you have to calculate. Okay, so here so there are some details that I do not want to go to, but so here these C's are actually, the tau is a imaginary time. So if you have not learned this imaginary time Green's function yet, probably you will learn in week 5's lectures. But I'll talk about imaginary times probably in the next week. But let's say these are some creation and analysis operators in imaginary time. Okay, so in imaginary time some calculations becomes very simple. But yeah, so this is just a theoretical, just a mathematical way of writing things. Okay, so this is imaginary time, and the contractions are actually given like this. So if I have something like this, time order of ck sigma tau and ck sigma dagger 0, then this is actually given by the Green's function, which is the imaginary time Green's function k sigma and tau. Okay, and this same thing is represented by something like this, a contraction. C K sigma dagger 0, and there is contraction. So this is also same as this minus G. Okay, so we'll try to just contract between dagger and undagger objects. So whenever we'll have something like some dagger, and if we do a contraction which is 0, this contraction is 0. And if I have some undagger, if this we do this contraction, this is also 0. Okay, so this is the main rule. These are the 3 main rules that we will follow, and we will try to write all possible contractions that you can have. Okay, so yeah, so now let's try to do that. Let me just copy this expression. Right, so let me make another copy. So okay, so what are the possible contractions that we can have? So we can have a contraction between this and this. So I say that we have to do a contraction between dagger and undagger ones. We can also do a contraction between this and this, right? So this is one possible contraction that you can have. So let me write that contraction, this and this and this and this. Okay, and so another contraction that you can have is between this and this and this and this. Okay, and you see that if you try to write any other contraction, all of this contraction will be either dagger or either undagger, so they will be 0 by default. So this is one contraction and this is another contraction. Okay, so now what we'll want to do is we'll like to bring this dagger and undagger objects close. So like we'll anti-commute them, and we'll just try to bring them close. Okay, so because there is time ordering operator already sitting here, so we can exchange these two operators, but with the cost of a minus. Okay, so because fermions, when you extend them, you get another minus. So what I would like to have is, so like for example in this first expression, things are already nearby, so I do not have to do a lot. Okay, but I'll have to flip these things, right, so that I have particularly this kind of a form, undagger and dagger. Okay, in that order. So I can just flip these things, that will give me minus. But here I'll have to bring this to here, right? So I'll have to do some kind of this anti-commutation, and this to here. Okay, so that these are nearby, and then we'll replace it with Green's function. So let me show you a trick how to do that. Okay, so this is simple. You can just manually flip these things one by one, and you can do that. But let me show you really a very handy trick. How do we do this permutations, and what is the sign of the permutation? Okay, so for example, let's just denote this thing as 1, 2, 3, 4. Okay, so these are 4 operators. I am just denoting them with 1, 2, 3, 4. Okay, and what I'd like to have is I like to have so this is my initial, what I have, initial configuration, and the final expression should be something like this 1, and after 1 I want to have this I want to have this 3, like, because that is a dagger 3, right? And then I have this I have this 2 and 4, but you see that 2 and 4 are actually, this is not a Green's function, so I'll have to flip it, so that undagger comes first and then comes the dagger. So then I'll put the 4 here, and then I'll put 2. Okay, so is that fine? So I initially started with this configuration 1, 2, 3, so I named it to be 1, 2, 3, 4, and then I wanted 1 and 3 close, so I am writing 1 and 3. Okay, so I have to do this permutation so that this 3 comes in and 2 goes out, and I have to also write this 4 and 2 so that this contraction gives me Green's function as well. Okay, so yeah, so when we have just listed down what is our initial and final and what is the target configuration that we want to achieve, so then we'll just regist it out. So 1, 2, 3, 4, so I'm just writing the list of these things, and again 1, 2, 3, 4, and let's say we just draw arrows, which thing goes to where. So 1 actually doesn't change place, 1 is actually staying here, because in the same place, because we're not actually moving 1. But then if you look at other things, 2 actually goes to yeah, okay, so okay, 2 goes to 3. Okay, so like I'm just following this, 2 goes to 3, and then 3 goes to 4, so 3 goes to 4, and then 4 goes to 2, 4 goes to 2. Okay, so now let's say you have this kind of diagram. Okay, so when you have this kind of diagram, now what you have to do is you have to count that how many crossings are there. Okay, so for example, so there is, this is one crossing and this is another crossing. Okay, so there are two crossing, and for each crossing you will put a -1. Okay, and then, so because there are two crossing, so it is generally number of crossing, -1 to the power number of crossing. So here the number of crossing is 2, so this is just 1. So after doing a permutation you will not get any sign. Okay, so this is a, I mean, very useful trick when you have actually large string of operators. I mean, this will save you a lot of lines of algebra. Okay, so this is, you have to just count, okay, in this between two configurations, how many crossings are there, and then you will just have to I mean, raise that -1 to the power that number of crossing. Okay, so we see that here this thing, all the, after doing permutation, it doesn't give you any sign. So we'll just write this as something like this. So contraction between c k sigma tau c k prime sigma prime tau 1 dagger. So this contraction, and then I'll write c k prime sigma prime tau 1 and c k sigma dagger 0. Okay, so I mean, I am just left with this. I do not have any other signs. Okay, so I'm just writing this term 2. So let's just call them term 1 and term 2. So the term 2, so the first term will give me a Green's function. So I'll have a minus, so k sigma and let's say tau minus tau 1. So let me write it, and so k sigma tau 1, yeah, it's fine. And then I have this delta uh, k prime and delta sigma prime. Okay, so when I'll contract them, so I'll have to make sure that, okay, these have the same quantum numbers, otherwise these are 0. So that's why this Kronecker delta actually comes in. So these contractions will be non-zero if the sigma and sigma prime are there. Okay, so yeah, some simplifications. So this is term 2. Okay, and for the term 1, so what do we have here is, so let me just write it. So c k sigma tau c k sigma dagger 0, right? And yeah, yeah, so yeah, so contraction between these two, and I have, so let me just flip those last two operators, and I'll get minus tau 1 and c k1 sigma 1 dagger tau 1. Okay, this contraction. So this is term 1. So this minus sign actually came because I flipped these two. I flipped these two operators. Okay, so now you can actually write these Green's functions. So okay, both of these Green's functions have initially had minus, and this being plus. So the Green's function for this is given by g k sigma tau, and then this is given by g k prime sigma prime. So you see that tau 1 and tau 1 are same, so this is 0, but so you like to have because of some regularization is there, so you just write it as 0 plus, very small positive number. Okay, so this is your second term. So let's write all of these things together. So your a, which was this, so a which was this, we have actually used the Wick's theorem to write this in terms of this two terms. So this is the first term, and then there is the second term, okay. So yeah,
So I hope you got the steps right. Right. So let me actually, because this is important, let me actually recap this quickly. So I started with this string of operator, and so this is my rules of contraction. So if I have a undagger and dagger like this, then I'll put a minus Green's function for that contraction. Otherwise, if I have just dagger contraction and undagger operators contraction, I'll just write as 0. Okay. So then so we use this rule and we try to form all sort of contractions that we can have. So one term is this one, the nearby terms, and another term is like the far dagger one. Okay, so this one and this one. Okay, and for this one, so this one what we did was, so the initial configuration that we were starting with 1 2 3 4, and we'd like to have something like 1 3 4 2, so that this creation and annihilations are in the nearest neighbor, and we can write the Green's function. So I showed you a trick how to do that in terms of a permutation diagram. So I have 1 2 3 4. This is my initial, this is initial, and this is final. So the initial thing is 1 2 3 4, and the final is also 1 2 3 4, but this is a permutation, right? So 1 is not changed because 1 stays here. So 2 goes to 3 because of this, 3 goes to 4 because of this, and 4 goes to 2 because of this. Okay, now you count how many crossings are there, and you raise -1 to the power number of crossing, and so whatever you will get, +1 or -1, that is the sign of your permutation of this whole string. Okay, so now when you are done with that, so you just write those two terms. Okay, so that is as easy as that. So I mean, if you follow this principle, then you should be okay with any kind of operator contraction, right? So anything should be easy now. So is there any question?
Sometimes for same time number operator formation is done. That's again we have to give a minus sign, right?
Yes.
To make the creation in the different side.
Yeah. So okay. So what the question is? So if you have something like C dagger, let's say CI, so then
yes, sir. Because you are pushing to the right, but now we have to push to the left because again exchange is done, so extra negative sign will come. I think this for a Fermi loop or something they're saying.
So Fermi loop. So there is no Fermi loop as of now yet. Okay, so you are right. If you have fermion, so it is as if you are exchanging one particle. If you're exchanging the position, you will get a minus. But so what I am trying to say here is, so if you are asking about the 0 plus, so why there is a 0 plus, so that has a good explanation. So let's say you have any operator that you write is something like, let's say C, let's say some C alpha t and C beta t, right? So it is an equal time operator, right? C and t prime. Now if I want to take an expectation value, everything is fine, everything is all right. I can take an expectation value. If I know the time dependence, I can write the time dependence of this creation and annihilation operators. But if I want to reduce this in terms of a Green's function, then equal time is actually a problem. Okay, so equal time, equal time Green's function is not a very nice object, because at exactly t0, if you are at exactly t0, then you know that there is a heaviside theta function sitting in all of this Green's function, right? So at t0, so it has a step jumps. It is not a well-behaved feature, so it has a discontinuity. So we'd like to get rid of this discontinuity by introducing something like this. So what we do is first we create a particle on the vacuum. So like C beta is creating on a particle on the vacuum. So then we annihilate it. Okay, so even if that this time is same, but this time is like infinitesimally later than this time. Okay, so I mean, this is how you introduce this Green's function. So instead of the C alpha t, you just write a C alpha t plus C beta t dagger. And now this, I mean, you see that by doing this, I mean, adding this small infinitesimal positive number in this t prime, we can actually now write the Green's function. Okay, so this Green's function doesn't have a discontinuity because this is not at t0. So whenever we write this Green's function, the Green's function has two arguments, so like t plus minus t, right? So I mean, if you do the minus, so this is just a 0 plus. So 0 plus means very small positive number. So that's why you have 0 plus sitting around here.
So was
like
it
t tends to 0 from the positive side or from the negative
yeah.
side? There are
So
two options, right?
yeah, so there are two options, but I mean, why this is a natural choice to put a t prime? So because always remember that first you have a vacuum, so the expectation value, let's say, is taken on the vacuum, so there is no particle at all. So first you have to create the particle. So whenever you create it, let's name the time. So okay, at time t I have created that particle, okay, and then later at some point of time I am annihilating that particle, okay. So later, so the time later can be anything, right? So here if I say
Why can't I do this in the same time? I mean, what is it can't propagate? That is the reason.
no. So so normally, so so like when I showed you the Green's function expression, so Green's function, there is also a theta t minus t prime sitting here, right? So Green's in the expression of retarded, let's say in the retarded
Oh,
Green's
because
function,
of the singularity.
yeah. So
Okay,
because
got
not of
it.
this is not singularity, this is discontinuity. So the theta heaviside theta function is actually a steep function. So in some literature it says that okay, at t is equal to 0, heaviside theta phi is 0.5, and in some literature they will say that okay, this actually jumps from 0 to 1 directly, there is no in between value, okay. So we do not like this kind of discontinuity. So if we are trying to if we are trying to write the expectation values in terms of Green's function, then only we do this trick. So we will say that okay, the annihilation is actually done at a infinitesimally later time. So then our Green's function doesn't have this discontinuity anymore. So that I mean we can just write this as a g alpha beta 0 plus. So that is as far as that is the reason why people do that.
Yes.
So is that okay?
Yes.
All right. So any other questions? So okay. So let me So I need to talk more about diagrams, and so that you have a practice of how to write the expression for diagrams. So let me actually give you some examples. So you have already seen this kind of diagram in the lectures. So but let me write this anyway. So this is fast order when you have Coulomb interactions, okay. So this is the wiggly line is a Coulomb line, okay. So this is a fast order in the perturbation series of Green's function, right? So now let's say that we are trying to write the expression for this Feynman diagram, right? So now what we have to do is we have to follow some rules. So the rules are something like this. So each line has to have a momentum and frequency, right? And each of the vertex, like this one and this one, okay, it is okay, my screen is lagging a little bit. uh, okay uh, uh, okay, sorry, I had a small network issue. So I hope I am back. So you can see my screen, you can hear me as well.
Yes.
Okay. So yeah, we are trying to write this Feynman diagram, right? So so each of these lines represent a Green's function, and they have a well-defined momentum and energy or frequency, okay. So in each of these vertex you have to conserve momentum and energy, okay. So how do we do that? So let's say if I write it something like k minus q, and let's say omega minus some omega, okay, for this line, then this Coulomb line has to carry on q and omega, this energy, okay, and then I can end up with k comma omega, right? So I mean this actually takes I mean on all of the vertices energy and momentum are conserved. Okay, so you can actually so I mean normally for Coulomb interaction doesn't depend on frequency. So let's say let's for now remove this capital omega for now. So but it will have when you have a screening, then that will depend on omega, but that you will not talk about that now. So how do you write?
Sir, in some books I've seen like they've used a minus q, and in the lower
Yeah,
they give a plus k plus q.
yeah,
That is also,
yeah. It doesn't matter. I mean, anyway, so that also has a conserves momentum, and
and they're
this diagram
saying this is
also.
the unscreened exchange energy,
Yeah, this is
something.
unscreened, so that means this is just a normal Coulomb interaction. So for 3D, you have some it goes as 1 by q square. Okay, so but so these are terminology which we can talk about, but this is not important now. So this is unscreened Coulomb interaction. So you have interaction, then you can have some screening, which actually converts this to w, q, and omega. Okay, so then this is a little bit different function. And I mean, if we talk about linear response, then we'll look at this thing more carefully. So this kind of screening actually appears in some calculations. In literature, it is called RPA approximation. So we'll not be talking about that thing. That is a little complicated for now. So we'll leave that for future. Okay, some class probably. So yeah, so this is unscreened Coulomb interaction, and see, I mean, you can choose anything, any momentum, so that, but it just have to conserve energy and momentum at each of the vertex. Okay, so I mean, this is a good choice as any, like what I have written. So now what I'll do is, so let's say the yeah, so I'll just write this Green's function, right? So the single lines, these are just non-interacting Green's function. So if my Hamiltonian, if the bare Hamiltonian without the interaction is given by something like this, epsilon k c k dagger c k. Okay, so I am not writing the interaction, and so this is just the bare part of the Hamiltonian. So the Green's function g naught, so this is a bare Green's function, k and omega, this is given by like what I showed you in the beginning. So this is omega minus epsilon k plus I delta. Okay, so so this is the bare Green's function. So now let's write this expression. So for this line, so this is a bare Green's function. I'll write a g, capital G naught k comma omega. So this one I have written. So now let's write for this one. So this one is also a bare Green's function, but with a k minus q and omega, right? And then this one is also a g naught k and omega, right? So we have not finished. So then we have to write for this line as well. So this line is something like just v of q, right? So if you are working in the so odd orders, we'll have actually a minus signs, but yeah, so the minus sign, I mean, you can so just, so there will be minus sign. Okay, and also if there is so there is no Fermi loop. Okay, fermion loop will give you additional minus, but there is no fermion loop here. So now we have to remember that all of the undetermined momentum, so for example q, so this goes inside this loop, the q moves inside the loop, so this has to be integrated. Okay, so we have to just integrate over so in this whole expression we have to integrate over q dq, and for all of this momentum integral you will have just 1 by v just for normalization. Okay, so this is basically the Green's function for I mean, this is the whole expression when you write it from using Feynman rules. So I mean, as simple as that. So this is one example of the Green's function. So let me give you another example which is already you have seen. So this has a fermion loop. Okay, so this is also called a tadpole diagram. Okay, and this kind of a diagram which has a name which is called a rainbow diagram, so because of this wiggly line like looking like a rainbow, and this looks like a tadpole, right? So this is called tadpole diagram, and these are related to Hartree-Fock approximations. Okay, so this if you are curious, that this is the Hartree term and this is the Fock term, okay, which is used to approximate Green's functions. Okay, so probably we'll talk about it at some point of time, but let's first look at this. How do you write this? So this line has a, let's say, k comma omega. this also has a k comma omega, and so this has a q comma let's say something like some omega. Okay, so and so you see that because I have to conserve momentum at each of the vertex, so this line has to carry a momentum of 0. Okay, there is no other option. Okay, so yeah, so now we can write the Green's function. So for these two lines we'll write Baire Green's function, and for this whole loop also we'll write a Baire Green's function. So let's just write this. So g naught k omega and g naught k omega. With that I'll write a v of 0. Okay, so v of 0, so let's not I mean look at this thing very carefully, but so let's say this is a v of 0, and then I'll have g naught of q and omega. Now we see that so there is actually a momentum and frequency which is going around the loop, and this is undetermined, so this can be anything, right? So for that we'll have to do integration over both of these q and omega. So this only depends on q and omega, so I'll do a dq d omega and have a v times 2 pi, just for normalization, right? And now you see that so this is a first order in Coulomb interaction, so I'll put a minus here, and so because there is a Fermi-on loop, that also give me a minus, so this becomes a plus. Okay, so this is your expression basically. So yeah, so this is your expression. Okay, so is this okay? Any comment, any questions? So now the work is you plug in all of these things and you try to compute. In most of the cases you cannot analytically do a lot, so then you have to take help of a computer. Okay, so we'll not calculate this explicitly, but just to give you some idea how do you work this out. Yeah, so any questions?
In the above term, energy is also deducted, right? Omega minus some omega dash or something.
Yeah, so I mean you can think about that, but the argument so yeah, so you are right, so it should be omega minus omega, right? So this should be omega, but as I said that the Baire Coulomb interaction doesn't depend on frequency. So what depends on frequency is the screen Coulomb interaction, which is not here. So I mean you can write this with q omega. Okay, and you will see that with this vq that you write, if you want to incorporate omega, that has to be delta omega comma 0. So omega has to be 0. I mean there is no other frequency dependence in this Baire Coulomb interaction. Okay, so if you you do that, you introduce omega and you do this integration over omega as well, you will see that you will get down to this equation only.
Okay,
right?
And sir, again, sir, Taylor, why the q is 0 for the Hartree term?
Yeah,
I did not.
so you see that, I mean if you want to conserve it, so you see that so my incoming and outgoing line has to have the same energy and momentum, so energy cannot get lost in the system, everything has to be conserved, so whatever is incoming I should get that out. Okay, so that cannot go anywhere. So if you want to have this kind of incoming and outgoing k omega, you see that what is the, so let's say you put something like here, okay, q. Okay, so what you have to have is, so incoming k, okay, incoming k is equal to outgoing k plus outgoing q, right? So you see that q is actually 0, right? So if you solve this, you see that q is actually 0. So for the Hartree term, only option you have is q is equal to 0. Okay, so Hartree term can be there, so in some, because we are talking about the most simple case, so q can have some finite values if you have some nesting in the Brillouin zone. Okay, so that is something that we are not thinking about, but so we are thinking about just a very simple system. So in this case q is just 0, so Hartree term, the momentum has 0 q dependence. Okay, so normally for homogeneous system, so like when you think about a system like a homogeneous system like a Jellium model, so in that case the Hartree term actually cancels the positive background, so there are a lot of positive ions which are fixed, right, and which also exert some potential onto the system. So this Hartree term actually is exactly same as those positive of the interaction with the positive charges. So this actually cancel with the positive charges. So we don't actually take this Hartree term, this tadpole in normal studies of homogeneous system. So yeah, just I wanted to put it out there. But yeah, so this is how you write the Hartree term. Okay, so you can have many complicated diagrams as well. So let me show you another diagram. So so this is actually very important when you have so when you talk about linear response. Okay, so let's say I give you a diagram, so we can talk about it later, how does it appear, but let's say I just give you a diagram like this. So this is called a polarization bubble. So this dashed thing is actually coupling to the external fields. So in the so you don't have to think about what those are. So what it does is it actually gives you a q and momentum. Okay, and same thing has to go out of the system, right? Because everything is conserved. So q and omega will have to go out. Now we are left with this single loop, right? And there is no Coulomb interaction in this thing as well. Okay, so now how do I write this thing? So as you can see that these are two bare Green's functions, right? So for those things I'll write a Green's function, but before that I'll have to give this momentum and frequency index on each of these Green's function, right? So for example, let's first write the momentum and frequency for this one. Let's write it as k comma omega. Okay, so you see that k comma omega, I mean this Green's function has a k comma omega, it comes here. Now this and this has to be summed up, right? So that momentum is conserved. So this vertex has to have some k plus q and omega plus capital omega. Okay, so I mean you see that what I'm trying to do here is, so this is k omega, and I mean in this vertex we are inputting this, we're taking input of q comma omega. So if you want to conserve momentum and frequency, so you have to do k plus q and omega plus capital omega for the other line. Okay, and again, so in this thing you get rid of this q and omega which you have added here and here, then you are again back to k comma omega. So this is the, if you want to have a conservation, this is what you can have. So there is no other there is other choice, but this is good as any other choice as well. So now I can write I can just write this thing, right? So so now here I have this g k comma omega. Okay, so g k comma omega is this thing, right? And so this is actually just an identity operator for now. So if you want to calculate current correlation which appears in the conductivity calculation, then this will be current operators. If you want to have calculate density correlation, this will be density operator, which has a matrix element of identity, right? So we are just thinking about density right now. So this is gk omega, and then I'll write gk plus q omega plus omega. Okay, so now in the case when I have some internal degree of freedom, I have multiple number of bands. So then these Green's functions are actually matrices. Okay, so then this is just a trace. Okay, so why this is a trace? So we see that from where we are starting, we are actually coming back to that point. So that is exactly what a trace is. So I am starting from some vector alpha and I am coming back to some alpha and some over alpha. Okay, so this is what the trace is. So this is just a trace. And now let's also integrate out this internal variables which are undetermined. So then I will have dk d omega, and I can have v and 2 pi, something like that. Okay, something like that, or let's say 2 pi to the power d plus 1 if we are talking about in dimension d, and the plus 1 is for the time dimension. So we have this 2 pi d plus 1 for normalization, so because this is a Feynman loop, right? So then I should have a minus included also in this expression. So this is basically the diagram. I mean, this is what the Feynman rules tell you. Okay, so this is the full answer of this diagram. Okay, so any questions, or if you want me to repeat, that is also fine. So is this okay? All right, so this is generally how you calculate a correlation function diagrammatically. Okay, so diagrammatics actually makes your life a lot easier. So I think it is already 7. So I had some other things in mind, but let's not do them today. But so actually let me actually give you one thing, so that you have a because you stayed for so long, so that you have some you can easily solve some problem of the assignment. So let me actually give you one thing. All right. So yeah. So very quickly. So if you have a Matsubara frequency summation like this, 1 by beta and I omega n and 1 minus I omega n minus, let's say, something like a, okay, or maybe say a, in place of a you can put energy or something like that, but let's just take it as a, okay. So then if this I omega n are fermionic frequencies, I2n plus 1 pi by beta, so these are odd fermionic frequencies, right? So then you can actually write this thing as an integral, okay. So how you can write this in integral, probably I will show you around next time, but you can actually write this in terms of integral. So something like this, 2 pi I dz, and then this thing, so you replace I omega by z minus a, and then you also plug in Fermi function, okay. So I mean you can, so people who have done contour integrations, complex analysis, you can clearly see this where this is going. So this will just become f of a, okay. So because the residue is just simple pole, I mean the a is your simple pole, and you can calculate the residue very easily. So this is what your answer will be if you have Matsubara summations, okay. Okay. So instead of this, if you have something like not fermionic frequencies, if you have something like so nu n, these are bosonic frequencies, so you can also do the similar thing. So there you will also get the similar result, but you will have an additional minus. So additional minus is there because Bose and Fermi functions have actually different residues. So so this is a Fermi function, and this is actually boson a, okay. So these are actually, so how you write this occupation number of fermions into a Matsubara frequency summations, okay. And this is how you write an occupation of bosons into a Matsubara summations. So here I nu n are even frequencies, 2n pi by beta, okay. So probably next time around I'll show you why this structure is there, but probably this will help you to solve one of the problems in your assignment, okay. So any questions? Okay, so if not, then we can stop here for today, and next time then we'll talk about some more problems as well, okay. So okay then, so have a good weekend, and I'll see you next time, okay.
Thank you.
Okay.